data, not actually doing the transmission. Leave that to Hacker transfer or TX samples from file if you've got a usurp, because you've got lots of money to spend. A little bit of theory that I'm just going to skate right through. A bit of code and a live demo that demo got admitting will work. So, is that readable?
We can do it another way. Let's try this. Can you hear it testing now? I'll put my phone in front of you, Russ, and then we should be able to hear. Here.
This claims I'm doing sound.
It's okay. We can do it through my phone.
Yeah, cool.
Yeah. Apologies, internet. We just had audio issues.
Okay, so so we do a bit of setup of the actual data we're going to transmit, setup of the radio parameters, the details of the high and low frequencies for transmission, and then the actual interesting part is that there's really not much to it. And I'm going to go through and show you, cover why it works, and then demo it. So why might you actually want to do this? So perhaps you've got a device that the official transmitter has a couple of different opcodes that it uses, but there's unused space in the opcode range, and you go, well, what's the receiver going to do? It receives something that's not documented. Debug mode, crash, who knows? Well, you might want to find out. Perhaps you've recorded something in the wild that you want to replay, but the SNR is garbage. So here, looking on a waterfall, you can make out the bit pattern for this direct SK transmission, but there's like replaying that against any target device isn't going to work because there's
There's a button.
Okay. Hey. But replaying that against a target device, you're not going to get anywhere because there's no signal compared to the really crappy noise floor. Maybe you want to use something like Open Sesame against a fixed code access system that you have completely legitimate and run it on, so you go, well, okay. Yeah, so, and in the end, you don't want to be messing around with the radio just to put together a flow graph to transmit to a handful of simple modulation data. So I'm going to jump over.
What batteries are they? Hopefully AAA.
Great. Green is good. So I'm going to jump over all of the Y and just do the practicalities. If you don't know, or if you haven't got an understanding of how, or, what the IQ data samples are and how radio signals represented in the complex plane, go and watch Mike Osmond's movies because they're great and they'll explain a lot of that. So the goal of the end transmission, 2FSK, so it's a simple digital modulation with two frequencies, high and low, used to represent 0 and 1 bits. The packet starts off with a preamble of alternating 0 and 1 bits, which you use to let the receiver know, hey, there's a transmission on the air. And some smarter receivers can use that to synchronize their clocks up as well. So if the transmission rate, the simple transmission rate, isn't exactly the same between the transmitter and the receiver can tell from the long preamble of alternating 0, 1 symbols what to adjust its reception clock. Then a synchronization word, which is a static, effectively an address that's used both for the receiver to go, this transmission is for me, and also so that it can detect the end of the preamble and the start of the actual data. So in this example, the sync word is X0C4E, and then the actual data packet, which I'm using an ASCII string, transmit. So the final packet that's transmitted is hex A is a 1010 pattern. So we have a sequence of alternating 0 1s, the synchronization word, and then our final data packet to show that we are go there. So we're going to be generating a set of samples for IQ data, representing position of a point in the complex plane as it spins around the origin at varying speeds. So high speed, high frequency, low speed, lower frequency. The rotation speed around the origin in hertz, so cycles per second, rotations per second, is the frequency of the signal offset from the transmission frequency of the radio. So if you have your radio set to say 433 megahertz, and then you spin your point around the origin at 1 megahertz, the final signal will be at 435 megahertz. And then slightly faster, high frequency, digital 1, slightly slower, low frequency, digital 0. The center frequency is the tuned frequency of the radio. For 2FSK data, you'll see a couple of peaks offset from that for the 0 and 1 bits. The signal frequency is the center of that double peak pattern. Signal offset is where we're offset from the amount we're offset from the transmission frequency of the radio. For 2FSK data, the signal deviation is the amount from the transmission or from the signal frequency that the high and low bits are offset. What we need to know though are the offsets of the high and low frequencies from our transmission frequency. So the rotation speed, or the frequency relative to the transmission frequency on a 0 bit is the offset of the signal frequency minus the symbol deviation, and 1 bit is the offset plus the symbol deviation. And so, yeah, these are measured in hertz or rotations per second around the origin. We also need to know some stuff about the transmission data rate. So the sample rate, when you're configuring your radio to transmit, you can say transmit at, say, 20 megahertz. So that's sending out 20 million samples per second, sample pairs per second. I probably shouldn't, that should actually be baud rate rather than signal rate. So that's the number of digital symbols transmitted per second. I'm just going to transmit a nice slow 300 baud, in this case, signal. And in order to generate this data, we need to know how many samples are transmitted for every symbol. So here, as a much lower speed example, say the entire transmission of 4 symbols is 1 second long, and we've got 12 samples for the green ticks over that period. We have so 12 samples per second total, 4 symbols over that 1 second. So we see 3 samples per symbol. For the actual transmission, it's going to be 20 million divided by 300, which gives us a much higher symbol length of 66,000 samples per transmitted symbol. So for every sample we transmit, we need to spin our point around the origin by a certain amount. So we increment the angle theta, the point is offset, or the point is shifted around the origin. Everything up to this point has been in hertz, so that's cycles per second. Every symbol we transmit, because all the math routines use radians, so to change from hertz, rotations per second, to radians per second, we multiply by 2 pi to get radians per second, and then divide by the sample rate to get radians per symbol. Sorry, radians per sample. And then for every sample we send out, we just spin our point, find the I and Q values, so in phase and quadrature, or X and Y on the sample plane, on the complex plane. So find those X and Y values, pack them into binary data, which for the HackRF is signed 8 bits, so it's signed characters. If you've got a better radio, that'll be floating point, and you'll have much less quantization noise. And keep on going until you run out of bits. So, and again, that's going to be difficult to see. We set up preamble, is that hexadecimal sequence of 0 1s followed by the synchronization word. Our actual message. And then at this point, just unpack that into a string of 0 and 1 characters, because that's easier to deal with, because the list are all been done. Sample rate, 20 megahertz. The rate we're going to be sending samples out to the radio. The frequency at which we're going to tune the radio for transmission. So that's the 0 hertz at baseband, and there's that's difficult to use due to the DC spike because of calibration offset on the ADC. Sorry. The actual frequency at which we're transmitting, or we want our signal transmitted. The 2FSK deviation, so that's the amount by which the high and low values are offset from the notional signal frequency. And then the baud rate of the transmitted signal. 2 pi. If anyone says tau, I won't talk to you because tau people are annoying. Samples per bit. Easy.
No, it's staying. Let's learn.
Samples per bit, as I said, is just the sample rate divided by the signal rate, so we know how many samples to generate for every symbol we transmit. offset in radians per sample for 0 and 1 output bits. Again, it's the signal frequency minus the center frequency, so that's the offset of our transmit signal from 0 Hz of baseband, either plus or minus the deviation, and then multiply by 2 pi, divide by the sample rate to get that in radians per sample. Start at an arbitrary offset, 0. Hey, that's cool. The amplitude is relative to the, well, not relative, but is scale within the range of the transmitting radio, like RF, 8-bit DAC. So the maximum offset above and below 0 is 127. 100 is close to that, and not going to be plugging anything. And then message bits is that string of 0 and 1 characters that defines our message. For every character in that, which is a bit to be transmitted, we count up to the number of samples per bit transmitted, increment the rotation around the origin, find the values of the in-phase and quadrature signal, which are the X and Y values, pack that into a binary data structure, so that's just 2 sequential signed characters, and print the output. And then that output data can feed to HackRF transfer or whatever, and get your transmission. So now comes the part that also may or may not work.
Do you want me to hold the microphone?
Sorry?
Do you want me to hold the microphone?
No, so this is that Perl program, the little thing that it is. So just generate a that contains that find, and I'm receiving with RFCAT, which is a little thing that has a lot of digital reception, both transmission and reception built into it, which also helps to avoid dealing with new radio. So I'm just setting up the receiver here to say, yep, we want to receive a signal that we expect at 433 megahertz exactly. Receiving packets of 10 bytes. The data rate, 300 baud. The sync word that I'm using is the default sync word in RFCAT because I'm lazy. And then let's listen and actually receive that data. And in order to transmit it, that. So down here, we've got for that transmission, that's this little dongle over here, which you probably can't see. Okay, so using HackRF transfer to actually send the data out. And then when we transmit, much faster would be better.
Yeah.
Hey, and then so, that's not this wrong.
Still works.
Yeah, so the slides will go up on wherever Pam puts them. Feel free to take a photo of that, or come and ask any questions if you're interested in doing it the slightly harder way that means less dealing with annoying software. Cheers, thanks all.
Thank you very much. Do we have any questions? So,
Why do you find your new radio so annoying?
It's just it's big. I'd much rather, you're either writing a bunch of Python and putting together blocks and all of that, or you're messing around